Hey, this is Don from Padlock Technologies here with another whiteboard video. We are going to talk about optimal route reflection. This is a technique where, you know, for someone that has route reflectors or you're running BGP with route reflection in your environment, you would probably do this to, better optimize traffic based on certain criteria from the route reflector. So, first things first, why would we do any of this? So let's start talking about optimal route reflection. So they call this ORR for short. ORR, optimal route reflection. So if you're running BGP, and everybody knows about the full mesh rule, which is, n parentheses n minus 1 divided by 2. So that will tell you, and it's the funny thing about that formula, by the way, total side quest on this, is that's the same formula used for symmetrical key encryption. So the same thing for the BGP full mesh requirement is the same numerical calculation for symmetrical key encryption. So back off the side quest. So what is this for? So the whole point of this is if you are running this topology, let's say you had 3 egress routers, and then we got some CEs down here, and the yellow ones are going to be route reflectors. Let's say the route reflectors here. So in order, and we'll just create some networking here. Let's make sure I actually have one there, and then this one's here, same here, here, and here. So here's your egress, and let's say the internet is out here somewhere, and they're doing some peering. And then you have your route reflector 1, because you always should have 2 or more, route reflector 2. And then we have CE1, CE2, CE3. Okay. So from the internet, we're just going to take quad 0 for now. So quad zeros are coming through. So if you have a topology like this, and let's say you have people connected to the CEs, they want to get to the internet. The problem with this is the route reflector, when it's doing its route calculation and sending it to the CEs, it's from the view of the route reflector. So when these paths come in, the route reflector will run its calculation, and then based on the IGP metrics, we'll say, okay, this is the best route there, right? This is the best route there. The problem with that is that might not be the best route for any of these CEs down here. And that's the problem with using route reflectors. It causes suboptimal routing because the viewpoint is from these guys. And put suboptimal routing up here too. So we can just be a little, that's just nasty, but whatever. So we got suboptimal routing because depending on your route reflector placement in your environment, it may not be a good idea to route based on what the route reflector sees as the best path. So what suboptimal routing does, and you can only do this with a link state protocol, by the way, you cannot do this with a distant vector protocol. So be careful trying to implement this with a distant vector protocol because there are certain information that needs to be sent out. So what optimal route reflection does is basically, if you're doing OSPF, it runs the reverse shortest path algorithm. So by default, something like OSPF or ISIS runs the SPF algorithm, which stands for shortest path first. All right. So that's the generic link state protocol algorithm. So there's different versions of SPF, and I don't want to run through all of them, but we got RSPF, which is reverse path, and this is the key to optimal route reflection. Then you got ISPF, which is incremental. It's like if a part of the network breaks, it just runs the SPF algorithm on that part. So that's why it's incremental. There's CSPF, which is SPF algorithm. This is for MPLS TE, right? And this is going to run it based on constraints. So this is constraint, shortest path for algorithm. And once you create your constraints, basically your bandwidth constraints, all kind of constraints you can have in MPLS TE, it will run CSPF. But I'm really concerned about RSPF. And what does RSPF does? What RSPF will do is on the route reflector, it will actually run the SPF algorithm from the viewpoint of the CE of all of these. So it will say, hey, when I get these routes, before I distribute them down to the CEs or send them to the CEs, what I'm going to do is I'm going to run the SPF algorithm as if each of these CEs are the root, right? Because if you don't have this, then the RR runs it as the root of the SPF algorithm. So I'm the root of the tree, basically. And RSPF will say, nope, I'm going to say CE1 is the root of the tree. And then based on whatever the best or optimal route from CE1's viewpoint, I'm going to send that egress PE. And let me just put PEs up here. So this PE1, PE2, PE3. Now, the reason for this is in between this whole mesh here, you may be doing some manipulation of cost metrics. There may be certain links that are greater than the other one. So there's a bunch of stuff that come into play for that calculated cost. And the only way you're going to be able to get the optimal route reflection, that's the whole point of this, our optimal path, is to run it from the viewpoint, or the root is going to be the CEs and not the route reflector. Now, to do this, there is another address family that you have to run, because you're going to have to send link state information. That's the key in this. The link state information from the CEs to the RRs. And the address family is basically called, it's just address AFI. It's called link state. Now, the funny thing is you may have to put, depending on what version of iOS you're using, the iOS XR, it's actually address family link state, all right? So then when you activate the address family link state, AFI, sub AFI for us geeks out there, when you run that, what it does, it's going to send all this link information to each of the RRs. So whatever the link, the cost value, all that stuff is going to be sent to the RRs. Now, this is how the RRs, or the route reflectors, can now make that calculation to see what is the best path, because I'm getting all that information via BGP. Right, BGP can actually hold all kind of information, not just, IPv4, IPv6. There are VPNv4 routes, there's VPNv6 routes, there's MVPN routes, there's link state routes, or link state routes, there's EVPN routes, there's VPLS, which is L2 VPN routes. The list goes on and on and on and on and on of the AFIs and sub AFIs that they add to BGP. But this one here, link state is critical if you want to do optimal route reflection, because the CEs will send its link information to the RR, or the route reflector, so that it can run the RSPF algorithm to give it the optimal path to one of these PEs up here. That's the use case for this. Depending on your network, most people are not going to do this. You're probably going to see this at the service provider level. If they're running like sort of, normal BGP, or just global routing table kind of BGP stuff, or are they running things like SRTE? Because you have to set, if you're doing segment routing with TE traffic engineering, you have to with a PCE and a PCC. And I'm using a lot of acronyms, but the PCE is a path computation element, and then the PCE is a path calculation client. But basically that does is it's going to offload the path creation from on box to another element or another router that will do the calculations, and then it will send the path down to the PCE and say, okay, here's your path to get to this destination. But that is something totally different. I may do a video on that, on, you know, segment routing and the whole, you know, PCE, PCC concept. But this is something that you would do probably in a service provider and not in a campus network. But it is something, if you would try to do it, this will give you a optimal path if you're going to use route reflection, right? Now, if you're going to use clustering, you don't need to use ORR because you're doing clusters. So again, this is Don from Padlock Technologies. Hopefully this video was informative. Thank you and have a nice day.